so our plan for today will be first finish chapter 3, and then we will get on chapter 4. Right? So in chapter 3 so far we have studied the formulas, and so if I give you the formula, you can use formula to do some calculations. For example, you can calculate the molecular weight, or you can calculate the molar mass. So we studied those in the first few sections. And then in this section you can see if I give you the formula, you can use formula to calculate how much atoms in some of those given information. Right. So we started on this problem, and so I think over the weekend we work on this, and the answer is like this. I mean the procedures. So you start with grams, and those will be the typical few steps in these few chapters. You start with grams, and you convert into moles, into moles of the compound, the moles of C3H8O, and so then you go from there, and you will get the number of C3H8O. So then the question asks you how much carbon atoms. So then from the number of C3H8O, you will get the number of C atoms. So the first two steps, step 1 and step 2, is the typical calculation as I said in these few chapters. Then the last step, step 3, is new what we learned last Thursday. Right. So the first step, in step 1, you use the molar mass. Then you abbreviate molar mass as mm. And then in step 2, you use the then just abbreviate Avogadro numbers. Then in step 3, you use formula as conversion ratios. Okay, so I'm going to go through this 3 steps and see how we use them explicitly. Alright. So the first step, that means you start with 25.0 gram of C3H8O. So this is the given compound C3H8O, and use molar mass for this compound into the calculation separately. So I think you should be able to calculate the molar mass now if I give you the formula. So you have 3 carbon, so 3 times 12.01. Then you have 8 H, and 8 times 1.01. Then you have 1 O, so plus 16. And the molar mass is 60.11 gram C3H8O. So that is equivalent as 1 mole C3H8O. Right. So this first fraction that I circulated right now is from the molar mass. Right. So then the second fraction you're going to use the Avogadro number, which means for every 1 mole C3H8O, there is a 6.022 times 10 to the 23rd C3H8O. That as a whole. Alright. So then the last last conversion will be depend on the formula. So when we read this formula, like this formula, or these two formulas are the same, we can identify, I can write it here. So that means for everyone C3H8O, and as we said before, is equivalent to how much those different atoms. So you read the formula, you can say for every one, this formula as a whole, there are 3 carbon, 8 H. So equivalent, you can write 3 carbon, and if you call that will be an atom. Right. So this is the equation, and use this equation you can write a fraction in. So let me write a fraction here. So I have 1 C3H8O. I will have 3 carbon atoms. So close the bracket, we have that. And these are the 3 steps. The 3 steps, as I said, were the 3 fractions. And then once you have those fractions ready, run them up and check to see if they come out. You can see the gram C3H8O, gram C3H8O come out. Then more C3H8O, more C3H8O come out. Then this C3H8O, simply the C3H8O come out. What is left over is the carbon atoms. And that is what we want to find out. So then the calculation is probably straightforward. You use the calculators. So you get 25 divided by 60.00, 60.11, and then times 6.022 times 10 to the positive 23. Right? So then times 3. And you get 7.51 times 10 to the 23. And the answer matching closely as D, even though there is a number difference, but those are they were like those numerical errors, depending on what model mass you use. Alright, so I think I cannot emphasize enough especially these first 2 steps. In this example, we're doing this way. What it means, if I have gram, I will divide by the molar mass, get how many moles, and then I will get how many more. If I have more, I want to find out how much molecular we have. I will just multiply by this Avogadro number, and then I will get how much of this as molecular. And then last fraction is also important, because once you get how much this as a molecular, and use this 1:3 ratio, 3:1 ratio we get from here, and we get how much those individual atoms. Right? So that's very, very fundamental. If you want to get a good grade, good understanding, get less frustration, and study those fundamentals, so step by step. Okay? So these 2 steps, and I show you here again from gram to mole, from mole to numbers. It's very, very basic. And you can do the reverse, which means if I give you numbers, you can divide by this number, get how many moles, and then you can multiply by this molar mass and get how many grams. Right? So you should review those questions. Yeah.
Would it ever be where the last one slipped? Where the 1 mole over the amount of atoms?
This is not that common, but is what we learn in this chapter.
Okay.
Right. Any other questions? Right. So the last step, and we emphasize is new in this section, but what we use is those subscripts for each individual atoms. So when we identify here, C is 3, so therefore we have 3C, and we have 8H, we have 1O. And those ratios are very important, and if those ratio is from the molecular formula, then you not only know the ratio, you also know the exact number. If the number you get from the empirical formula and you only have the ratio. If I don't tell you, that's also a molecular formula. Right, so if I give you the formula, you learn how to use it, and I think in the next few seconds we are going to do the practice. If I give you some information about the mass ratios or the mass percent of those individual elements in the compound, and you do some of those practice and learn how to find out the empirical formula, and if I give you more information, you can find out the molecular formula. Alright, so let's go on to do some practice, find out the empirical formula. Okay? Now let's begin by emphasize the empirical formula gives the ratios of atoms in the compound. And those ratios that we see here, you have the 3 to 8 to 1 ratio. And those are the ratios. And you can think about that is three carbon atom to 1 molecular, or 3 more carbon atom to 1 more of the molecules. So the unit can cancel out, but what is important is you know in the empirical formula you get those ratios. Right? So let's think about those in this practice. Let's think about the ratio of atoms in moles. Right? So if we understand that, we know those empirical formula has those mole ratios, and obviously, as I said, you can understand that as atom ratios. But numerically they're the same, so let's stay with mole ratios. Right, so therefore, to find out the empirical formula is actually to find out the mole ratios. Right? And mole ratio is mole ratios. Therefore, you want to get the mole ratio, you have to know the mole. Right, so this is now the most important step we need in find out the empirical formula is to find out the mole of each element. Right? So moles of each element or each atom is the key information we need in this practice. In this exercise, you want to find the empirical formula, no matter what I give to you, and you have to find out the moles of each element. So keep that in mind. Now also, you will see in details, you don't use those moles directly as the subscripts or as the number ratio. You have to know how to use those moles. Alright. So now let's keep that in mind, and we will do some of those programs with different informations. So if I give you the gram, I mean the simplest program is I will give you the mole for each element. Then you can start with the mole and find the ratio for each element. Then let's go back and do like out one step. So that means I give you grams instead of moles. And then you know from the last practice, if I give you gram, you can use molar mass and find out the mole very quick. If I give you the gram of carbon, you can divide the gram of carbon by the molar mass of carbon, find out the mole. Right? Now let's make the problem even more difficult. I don't give you those grams of element directly. I will give you the percentage of each element, as in this example. So in this example, I'll give you the percentage by mass of carbon, of hydrogen, and of oxygen, and then again, the key step, the key information you need is the mole of each element. So what you can do is you can use the mass percent as a conversion ratios that we studied in the previous few sections and find out the mass of each element. So therefore, if I give you information like here in this particular example, not more, not a gram, but it's mass percent of each element, and you just starting with this step, convert the percent information into grams. So as I said before, if you already have the moles, obviously you skip all the steps. If you have the gram, you skip this step. And now if you have the mass percent, what you do, you assume you have 100 gram of the compound. Right. So I will write the steps on the PowerPoint, and then I will do the practice on this board. So if I assuming I have 100 gram of the compound, and the compound we don't know exactly what the formula is, let's just call that compound. Alright, so now this percent information tell you, for example, for carbon, for C is 60.00%, and this is actually equivalent as you review what we learned by those mass percent. It tells you something like this kind of fractions, what it means you have 100 gram of the compound, then you abbreviate compound as compound, and then you have 60.00 gram of C. So this is the information you can get from mass percent. Mass percent, which means 100 gram of whole, and how much part in the whole. You can use gram, you can use kilogram, depending on the other informations. I choose use gram because we know how to convert a gram into moles instead of kilogram into kilomoles. Therefore, so I write, even though in this percentage don't have any unit, so I choose gram over grams. And you add in some other informations. You can see if that's for C, then you will see gram of C over gram of compound. Alright, so then you can use this fraction as a conversion fractions. And here we assuming we have 100 gram of compound. So therefore, if I multiply by this 100 gram of compound and 60.00 gram of C, and now you can see the cancellation, the gram compound comes out, and the only unit left over will be gram of C, and that is the information we need. Right, so therefore we will have this 100 comes out, you get 60.00 gram of C. Right, so as I emphasized at the beginning of this practice, to find out the empirical formula is to find out the moles. So we're getting closer, we're getting gram now. And I think after these few chapters by now, you should be feel very comfortable. Whenever you see the grams, it's equivalent as you will find out the moles. You can simply take the gram of the compound or the gram of the element divided by the molar mass of the element. Alright, so we will do this next step, and we are just going to use the molar mass and find out the mole of carbon. Okay. Because we can see this formula here is just carbon, so therefore you find out the molar mass of carbon very easy. It's just 12.1 gram of C and 1 mole of C like that. And so then once you know that, you see this gram of C comes out, you get more of C. Alright, so let's figure out how much was that. So we have 60 divided by 12.1. I think it's about 5, but you get 4. If I keep like only 2 decimal places, from the calculator I get 4.995. So let me run that. for that. So that so 500 more requirement is what you get from the initially the percentage requirements. And you do the similar for the other elements. So we have 100 gram of compound, and the mass percent of H is 4.48 gram of H over 100 gram of compound. So same idea. You see, you have the mass percentage, which means you can add on those gram and then you see the concentration, gram of compound, gram of compound cut out, and 100, I mean, do also say is 100 cut out, so therefore you will get 4.48 gram of H. So as I said again, you want to find the mole, so therefore the next step is use the molar mass. And so that's very, very important few steps. You know the gram, you should be able to convert into moles. Just read the problem carefully, see more, gram of what and mole of what. Gram H, not H2O, not H2. Be careful. So this is just H. If I tell you it's H2, you will take 2 times 1.01. Alright, so 1.01 gram of H and then 1 mole of H. And so then you can see this gram H comes out, and we will get another mole, which will be the mole of H. So 4.48 divided by 1.01, right? So get 4.44. If I round to like 2 decimal places, right? And so this is mole of H. Mole of C, mole of H, you find out the mole for every element. Next one is the oxygen. So we start with 100 gram of compound, and for every 100 gram of compound, you have 35.52 gram of oxygen. Okay? And similarly, concentration, gram compound come out. The 100 come out, so therefore you will get, then just don't stream that, then just do step by step. So you get 35.52 gram of O, right? So what do we do? If I have a gram, I will get more. What I use? And what I use? Molar mass. Molar mass of what in this step? Oxygen, not O2, okay? Not O3, ozone. O2 oxygen gas, right? You want to get the molar mass of O, and just 1 O. So therefore you have 16.00 gram of O and 1 mole of O. And you do a very similar calculation, you get 35.52 divided by 16, and you get 2.22. So 2.22 mole of O, right? So that is about this step, okay? And I think I did a few steps together. Right? So I did 2 steps, assuming for that. 1 more step. So now I did 2 steps, so I converted those into grams. Yeah, I have the percentage, so I have this step here. Okay? This step here is converting to grams for each element. Then I continue on, I will just divide by the molar mass and get the mole of each element. Okay? Okay, any questions about these 2 steps? Good. So then what we do next step is using those mole to write a pseudo formula. Okay? So what that means, you will not really get the final result for the formula, and you have to do something else. So let's write that up. And so we want to write a pseudo formula, just use the mole for each element. So usually we'll write the carbon first. So carbon is 5.00 and H is 4.44, and then O is 2.22. Am I right? All right. Okay. Any questions? Okay, good. So then you do something else. So because this is just a pseudo formula, not the final formula. So what you do, you want to get the more ratio. You really want to get the more ratio, as I said, the empirical formula, the more ratios. And to get the easiest way to get the more ratio is to use the smallest more of all those elements and divide into all the more, including itself. And let's say in this example, we have 3 elements, and we have this more 2.22. We have that one is 4.44, and that one is 5.00. Right? So the smallest more is this one. What you do, you will take this more, divide into all the others. Alright, so this convert into carbon 5.00 divided by 2.22 and H 4.44 divided by 2.22 and then O 2.22 divided by 2.22. Alright. So then next step, you really do the divide, and so you take 5 divided by 5 divided by 2.22, and you get 2.25, right? So that is how you set up. Once you set up, you really do the calculations. So now I will write carbon become 2.25. Now that's really a ratio now. We're getting closer to the really final result. So you get 2.25, and then H, that's easy to say, 4.44 is exactly twice of 2.22, that will become 2.00. I keep 2 decimal places because that's what we have before. And O become 1.00. Now the technical part. So principally you understand those are the important steps. Okay? And so just find the more and then divide all the more by the smallest more. Okay? So sometimes the principle is easy, technical part is difficult. Okay? The problem is if you get something like 2.00, 1.00, if you run into 2 decimal places, and you can see probably you don't need too much thinking. You see that is closer to 2, that is close to 1. Okay? 2.25 is a little bit too far away from 2 or from 3. Okay? How far is closer? Is close enough? And we use this criterion like 0.1, which means if you get those ratios, let me use n for any of those nearest integers, okay? And minus the ratio you get. If it's smaller than 0.1, then you can round up or round off. Right? So this n standing for the closest, you just see like you have, for every decimal number there are 2 integers, one up, one down. So this 2.25 has 3 closure on the upper side and has 2 at the lower side. So you just use the closer one and find out the difference between the number that is closer to your ratio, and then you take the average solution value. If that difference is less than 0.1, you run up, run down. Now for our problem here, we get, as I said, this number 2.25 is closer to 3 on the top, and right here, 3 on the top and 2 at the bottom. And obviously 2.25 is closer to 2 than 3. Okay? So what you do, you will take 2 and then you minus 2.25, and that will give you 0.25, which is larger than 0.1. So if it's smaller than 0.1, you do the rounding. If it's larger than 0.1, you don't do the simply rounding. What you do, you have to find out a number you can multiply, and you can multiply onto those ratios, and then you change those numbers, change this 2.25 into a number that is close enough to an integer, which means we'll satisfy this condition. So what number you can use to multiply to make this those kind of number become like closer to an integer? What you can do in general, you just take those numbers, take those endings, okay, and 1 divided by those endings, and then you will find the number you need to multiply. Right? So in this example, your ending is 0.25. So what you can do, you can simply take 1 divided by 0.25, and which obviously becomes 4. Okay, so then you can just use this 4 and multiply onto all those ratios here. Okay? So the ratio here, right now, we cannot do the simply rounding to 2 or rounding up to 3 because it's too far away from both numbers. So what we find out, we just take this 0.25, okay, or we take 1 divided by 0.25 and get a 4. Right? So then you will multiply every those ratio by 4. Alright, so if you do that, you will have a C 2.25 times 4, and H 2.00 times 4, and O 1.00 times 4. Right? And what you get will be C C9, because 2 times 4 is where you find them out. And then H will be 8, then O will be 4. Alright, so if some other time, some other problems, if you get those numbers, for example, if some of those ratios here, okay, is not like 2.25, okay, these are some other roundings, maybe some other endings, so I will show you those numbers. You might end with 0.5. If your some number is some 0.5, no matter what 0.5, 1.5, 2.5, 3.5, as long as you have 0.5 in it, okay, so then you want to find a number to multiply all those ratios and change them into close enough, you can run down. What you do, you will take that, so x.5, which means you will take 1 divided by 0.5, and obviously that will give you 2. That means you will take 2, multiply onto all the numbers. If there are some number ending like something like 0.33, or maybe 1.33, maybe 2.33, the question mark means any number, okay? 5.33. And you forget about those integers, you take those decimals, and for example, you will take 1 over 0.33. Okay? So what you get is 3, which means you just multiply everything by 3. Right? Alright, so this is the technical part. Okay? Right, so our answer is right, right? So that's a few steps. Okay? So usually after a few practice, and you will feel like much comfortable with those kind of problems. Right? So this example I use here, it actually will show up again later on in the lecture notes. But let's see another example here will be different. So in this example, actually a little easier because I did not give you the mass percent. I will just simply like going straightforward, give you the grams. Okay. So therefore, the first step we can skip. So this step we can skip because we don't have the mass percent. So you can just simply going from the grams to moles. Okay? So I will just going from gram to moles. Let's see for N. Okay, we have 24.5 gram N, and I think you are very quick now. Tell me what you use if you want to go from gram to mole. Right? Use molar mass. Okay? And molar mass of what depends on the problem, depends on the formula. Now this is model mass of n. Right, so what you do, you are just go to the periodic table, you find out for 1n, not 2n or 3n, is 14.01 gram. So therefore we will have 1 more of n, like that. And so this becomes very easier because you don't have to use the first this step, you don't have to figure out how to use the mass percent. And you take 24.5 divided by 14.1, and you get 1.75 more of n. So I keep two decimal places. Well, so whether I keep two decimal places or I will use like the technique we studied in Part-1, I underlining. So those I might not that consistent depend on the program. So you just know like so there's a little difference. Right. So for oxygen and the seminar we have 17.0 gram of O, and I will multiply by the conversion that also the molar mass, right? Just O, not O2, not O3, so we have 16.00 gram of O, then 1 more of O. Right, so you will take 70 divided by 16, and you get 4.38 more of O. As I said in the beginning of this class, getting the more is the most important step in those kind of program, which means find out the empirical formula. Okay? No matter what information I give you, now for this chapter we kind of narrow down. We just say how you get more from the gram. And as you learn more chapters, you will see there are many different ways to get more depending on the information. Right. Now you cannot use more as the subscript and say that will be the final formula. So when you write, usually you will write out the pseudo formula. Right. So the pseudo formula for this example will be N 1.75 and O 4.38. Right, so the next step, find the ratio. And the easiest way to find the very nice ratio is use the smallest mole divide into all the other moles. And in this example, the smaller mole is 1.75, so therefore you will take 1.75 divided by 1.75, you will take 4.38, also divided by 1.75. Right? So then this will give us N, 1, and O, 4.38 divided by 1.75. Okay, so you get 2.50. Okay, 2.50. Now let's examine this 2.50 again. Okay? So 2.50 is smaller than 3 and larger than 2. So it's in between these two integers. Right? You take either one, because this is in the middle. So let's say if I take this 2 as in this formula I write as our n, so then I will subtracting by 2.25, then I will take the absolute value, this bar means absolute value, and so what you get is a positive 0.25. Now our comparison, our criteria R is this number, 0.1. Right? If you find the difference between the closest integer is less than 0.1, then you can simply rounding down or rounding up. If more than 0.1, which means use the technique I told you. Okay? You will examine that number that is too far, and this example is this. And this has the decimal part is 0.5. 0.5. What 0.5 doesn't matter. 1.50. So this, since this 0.5 comes from this number, right? I think you already get it, right? So just take that number, or take 1, 1 divided by 0.50, and you will get an integer. Usually the problem gives you nicely, and you take those decimal parts, and take 1 divided by the decimal part, and you should get a number that is very close to an integer. And then you just use that integer, multiply on everything. And what you get is 2, right? Right. So therefore, let me circle this. I will multiply this formula by 2. And later on, I will tell you again sometime you need to multiply by some other number again. Okay? But right now here, we multiply this formula we get by 2 is because one of this ratio is too far away. You cannot simply run into 3 or run into 2, right? So therefore, you will get the final result. Let me write here. So I just write that too much space there. So you get N2 and O5. Right. So that will be our final answer. Any questions? Okay, so I give you all those number here, and you can just use that, and you can also just use what I said. What's this? Right, so this one we did before, right? Which means I will give you the mass percent, and you take the mass percent and convert them into grams. Right, so let's do a practice. I give you those information. Very similar as the first example I did. Remember this answer. So what's okay? What do we do first for this CRE? By assuming 100 grams of the compound. So you have B. And let me see your calculations. Where's you get the mole by the mole has 12 for carbon. You get that number. Okay. divide all of them by the smallest one. Getting them all just right away, getting very close to 7, 8, and 21. Yeah. Everyone get a B? Who's gonna get a B? Okay, I see in the first one, some probably, you have to use some more mass of carbon, right? Just, so just be very careful. You just write out, get the graph of each, yeah, that looks reasonable. I think N is like 0.72 is the smallest one. You gotta take all the other more divided by 0.72. I think it's okay, good. So you can see, this is not really like 7, this is not really 8. But you take a 6.99, that's close to 7, right? So you will take 7 minus this number, what you get is much smaller than 0.1. If more than 0.1, so just use what the technique I told you, take 1 divided by those numbers, and most of the program give you just that enough. Otherwise, you can look at the table. No, that seems to be in the wrong one. Very good, very good. Yeah. No, oh, then you forgot 9, that way what you get, right? Yeah, that's another possibility to make some mistake. Don't forget any element. Very good, very good. I can see that. Do you get that too? That number is not right, that's the problem. So then, 14. Oh yeah, you forget number less than 1, so I can get more than 1. So you have 10 less than 14. You did something wrong here. You get 1.00. Take a 10 divided by that, and see what you get. Alright, it's the next. Any questions? Okay, that's getting close, that's getting close. Good, good. Once you get it more right, that's the very, very important step. Right? Did you get it right? Did you get a B? You get a B? Alright, so just don't forget, once you get more, divide by the small. Okay? Right. So the answer is B. I saw most of you did pretty good. Okay? So then let's see the next problem. Next problem is to find out the molecular formula. Okay? So as we said before, sometimes the molecular formula and empirical formula are the same. Sometimes it's different. Okay? So that what you can get is a conclusion from compare the empirical formula with molecular formula. Okay? So what you find out is you can multiply the empirical formula by a whole number, then you will get the molecular formula. So that's what we say in this statement. Okay? The molecular formula is a multiple of the empirical formula. Okay? So in other words, if you have the empirical formula, okay, so if you have the empirical formula, okay, and then you put that in parentheses, and you can multiply by some number n, okay, and you will get the molecular formula. And you abbreviate that as a molecular formula. Now this n is an integer. And so this n is an integer. It can be 1, 2, 3, and so on. Now in the real programs, the number you will get from the information, you will try to get what is that n, and use this information here. If you use this information, try to get that n, and that n will not be usually so so nicely like just 1, 2, 3. So again, you will have to do a problem. Maybe you will not get 1, you get like 1.001, and you will not get 2, you will get 1.995. But the problem here will not make that more difficult. So it will be close enough, and you can simply round up and down to those integers. Okay? But as I said, it will be not that's real life, not that exact as that 1, 2, 3 like that. Right? So you just identify, you just remember if you have the empirical formula and you just use this formula to find out that n. So once you have that n, you just take that n, multiply onto every subscript of your empirical formula. That's what we mean by here. Right? So if I find out, for example, my empirical formula is CH, like that. My empirical formula is CH like that. Okay? Now, if I find out this n equals 6, right? So now, what do I mean by multiply by the line on the top? Multiply the empirical formula by n like this. You will take this CH and multiply by 6. Now what we mean by that is you multiply that subscript of each atom. So when you write CH, which means you have C1, H1. So what you do, you will take this 1 for carbon, multiply by 6. And that becomes 6. So therefore you have a C6. That's just example. Okay? I just come up with example to help us understand what we mean by this step. Right. So then the H also becomes 6. So that's what we mean by how to multiply. So therefore, the key step in this section is to find out this n. And then let's look at this formula carefully. So what is the information we need to find out this n? The information we need is the empirical formula. Okay? So I assume you'll be able to find out the empirical formula from the last few programs. Okay? And the other information you need is the molar mass of the compound, or molar mass of the molecular formula. Alright. So let's examine that a few steps with more examples. So you want to find out the molecular formula from the empirical formula and some other information. Other information will be the molar mass of the compound. Okay? Molar mass of the compound. Molar mass, let me write here, see the same, molar mass of the compound equals molar mass of the molecular formula. Right? So you understand those different names. So you need that in the last slide to find out that n. In the last slide, I tell you is the molar mass of the molecular formula. Okay. But sometimes the program will give you the molar mass of the compound. So then you know these two are the same. Alright, so this program, we know this information, so this equals this. And this formula is the empirical formula. Right? Right. So if you want to change the empirical formula, which is C2H3O, into the molecular formula, you need to find out what is our N. You will take the empirical formula, multiply by N, and then you will get the molecular formula. Right? So N will equals the, let me just use this, molar mass of the compound divided by the molar mass of the empirical formula. So this, both of this is abbreviation. So now for this problem, what is the molar mass of the compound? I would say it's 86.09 gram per mole. You agree? Okay. So we find out the molar mass of the compound from the given problem. Okay. So then divide by the molar mass of the empirical formula. Okay. So every formula has molar mass. You already know how to calculate the molar mass for H2O, right? Now for this empirical formula is C2H3O, even though it's an empirical formula, but it still has molar mass. That makes sense? Okay. So we'll see the molar mass of this equals 2 times 12.01, right? Because we have 2 carbon, right? Plus 3 times 1.01, so that is we have 3H. Then plus 1 times 16, and that will be our molar mass. You can also call this number molecular weight, depending on the unit. If you get a number, you see that is how much mu, then you talk about the molecular weight. So we have 2 times 12.01 plus 3 times 1.01, then plus 1 times 16. So I get 43.05. Because I said I'm going to calculate the molar mass, therefore I give it this unit. I give it like a gram per mole. If I tell you at the beginning, I want to calculate the formula weight, or the molecular weight, and then I will have here I have this AMU. Right? So what you do now, just take this number and has a unit, and then put it together, and let's see what you get. 86.09 divided by 43.05. Right? So this number changed into 2.02. So as I said before, so those numbers usually will be very close enough to some of those integers. Right? So you take this number, right? So this number will be less than 3, more than 2 again. And then what you can do is closer, much closer than 2 than 3. So you can see they just take a 2 minus 2.02. Then you take the every 3 value, you get 0.02, okay, which is much smaller than 1, smaller than 0.1. And therefore you can just simply, because the difference between the numbers and integers is so small, so this change into 2. You don't have to worry about use 2.02. Understand? Right, now we're almost there, so we'll take this, we'll take that C2H3O, so C2H3NO, then multiply by 2. And what that will give you is C4H6O2. And that's what our final answer for the molecular formula. Get it? give you an example relatively simple. Now I'll give you this practice CRE. You leave a digit cross, and you'll figure out where the digit cross is. In the example, I give you the empirical formula. Now here I give you the information, and you use information to find out the empirical formula by yourself. Okay, what do we do first? For this problem, what do we do first? One of those mass into balls. And then you will find the empirical formula, right? Yeah. So find the empirical formula first. I think that's probably our, not our first practice, so you should be able to find the empirical formula. When you find out, you did it at home? Okay, now do it again. Like I said, you do it one time, you have to practice. Even though you did get an answer, you can just you need to practice a few more times. What do we get? D. Okay. Where's your calculation? Where's your, so that is get more. Get more issues. Okay, any questions? Okay, let me see your work for the empirical formula. Where's the more for all of those? So you already converting into the ratios.
Well, that's the more mass.
That's the more mass of the compound.
Yeah, and then this is, it's just right here.
Okay, so here you get the more for each of those, and then you divide by the small more. That's, yeah, that's it. Okay, you have those. So this is the mass of carbon, right? Very good. You take that divided by 12 or something, right? Get more. You take that divided by 101. Yeah, then you find the ratio. The smallest one is 303, right?
Yeah.
Very good, very good.
So then it'll be then.
Yeah, and this one is 3.199. You can see it's so close to 4. Yeah, yeah. Then this is the empirical formula, right? Right, very good. Yeah, very good. So that's. All right. Any questions? So I think every step is easy, and you need to practice many times. Okay? Our first exam will come up pretty soon. So don't feel I did this question, I get the answer, and you will feel like okay with your exam. Okay? You will be really surprised because I emphasize every semester, every exam. Okay? If you don't practice many times, you just simply get an answer for one time, and I guarantee most of you will be surprised. Maybe it's not everyone. Okay. Right. So we will have another way to find out the empirical formula. Okay? So in this way, which means I will not give you directly what is the mass percent of carbon, what is the mass percent of hydrogen, what's the mass percent of oxygen, okay? Or even not give you what is the gram of oxygen, what is the gram of H, what is the gram of carbon. So I will give you something like the what we produce from the compound. Okay? So this is one technique. And so typically this works pretty good for ideally for any compound. So in this section we'll just emphasize for the compound that has, so this will be our compound. Okay, so this will be our compound. And you want to find out the empirical formula for the compound. You know, we studied in chapter 1 what is the compound. Compound is supposed to have like one unique molecular formula. And in that molecular formula, you will have more than one type of atoms. Right? And so we don't know this compound formula yet. But because we call this compound, so therefore we have a different element in it. And in this section, we'll see in this kind of compound, we only have this 3 possible elements. And this is the most complicated problem. And sometimes so this kind of problems is complex. And there are similar ones. You only have carbon and H in it, and that's very simple. But anyhow, your compound has these few possibilities. Maybe it has only carbon and H in it, and maybe the double cross has carbon, H, and O in it. So in the previous few examples, what I did, or what the book did, it will give you the gram of carbon, give you the H of carbon. You just simply use more math, get more, then you find more ratio, right? You probably just do a little more work, like say your ratio closer to integrals, you just otherwise multiply by some numbers. Or I'll give you the mass percent of carbon, mass percent of H, mass percent of O, and you going from there, you're doing more work. Right? Now here, I will give you totally different information. I said I have this compound, and I will take this compound in some of those experiments. The experiment, what we did is put the compound into a furnace, and then we will see the products. So the product we assuming is ideally we supply enough oxygen, and also the compound will be go through the chemical reaction, converted into either H2O or CO2. So then we will analyze how much CO2 we get and how much water we get. Then we know if our chemical reaction is complete, all the H will go into water and all the carbon will go into CO2. Because we don't know explicitly or exactly what is the chemical reaction equation, but we know our compound has C, H, and O in it. And so if I know what is the formula, I will write out those. But right now we don't know what is the formula, so we just write out like this. And then plus oxygen gas, and right. So then, if the reaction is complete, and what we have is only these 2 products. Only these 2 products. So no matter what that formula looks like, and then you will know if you supply enough oxygen and your reaction is complete, you will not produce CO, you produce CO2, and you have only these 2 products. If these only 2 products, by the law of conservation of mass, right? We don't create any new carbon, we don't lose any carbon, so all the carbon will get into these products. There's no carbon in the other products. All the H will get into water because there's no H in any other products. So therefore, by measure how much CO2 we get, and we can measure in gram or kilogram, but you want to use a gram. So once you know the gram of CO2, and you can convert a gram of CO2 into mole of CO2, right? And so then you can see if for this CO2 is simple because for each one CO2, for each 1 mole of CO2, this is the equivalent to 1 mole of carbon in that element. So that I said we are going to use those formula as a conversion ratio again. And then similarly, for every 1 mole of H2O, you can figure out how much more of H. All the carbon get into CO2. All the H get into water. Okay? Now you want to find out the numerical formula, which means you want to find out, you can even use some of those letters, you call them like, what is will be the number for carbon, you call that X. What is the number for H, you can call that Y. What is the number for this? So those will be our example. Is this example here, you have C, you have 9 for C, 8 for H, and 4 for O. But you don't know the number, but you know you will have some numbers, right? So all those carbon then will go into CO2. All the H, we don't know how much H, but we know they will all go into water. And you can find out how much H you have by using information of H2O, because all the H is in H2O. You can use the information of carbon and find out how much carbon in the initial compound. That makes sense? So then let's see how much in 1 mole of H2O, how much more of H? How much more of H? That is very, very critical in this step. So this will be the 2. You get the 2 from this number here too. Okay? You can use the formula as conversion ratios as what we did at the beginning of this class. Right? So once you have the mole of CO2, you can get more of carbon by using this ratio, right? And once you get more of water, you can get more of H by using this ratio. Now, how can you get more of CO2? Okay. So you can use the gram of CO2, and then use molar mass, get more of CO2. And the gram of CO2 you get is by that the last slide in those apparatus. You can see once you produce those products, you can absorb all those CO2 in this apparatus, and you can measure how much CO2 you get, right? So then similarly, how can you get more of water? Yeah, we can do a very similar step, right? You see in this picture, you get 2 products. What are the 2 products we get from this kind of experiment? What are the 2 products? CO2 and H2O. Okay, so what we did, what we used for the from the information of CO2 is use the gram of CO2, right? And use the molar mass of CO2, we can get more of CO2. That's what we use for one product. Right? Now what are you going to use for the other products? Water.
Grams of water.
Yeah, you can get, you can find out like from here, right? You can see how much water is produced. So gram of H2O. If you know the gram of H2O, right? If you know the gram of H2O, you will use the molar mass of H2O, find out the mole of H2O. Once you know the mole of H2O, you can use this mole ratio to find the mole of H. Is that okay? That makes sense, right? Now, what is difficult is if we have also oxygen in it, how can we find out the mole of oxygen? As I mentioned at the beginning of this class, the important information you want for the empirical formula is the mole of every element. So after these 2 steps, you already know mole of carbon, you already know mole of H, but you don't know mole of O. So therefore, after these 2 steps, you want to spend some time try to figure out what will be the mole of O. Well, the old story, right? So I think one typical story is that you can get more of one element by the gram of element. So usually this kind of technique is I will give you another information. Okay? So I will give you these two information. I will tell you how much gram of CO2 you produce, how much gram of water you produce. Another information is how much gram of the compound you start with. Okay, so you will know the gram of this compound. Even though we don't know exactly the formula yet, but I will tell you I use how much gram of the compound. And that is very important because you can use the gram of the compound and find out the gram of oxygen in this compound initially. You cannot use those information to find out the gram of oxygen in the initial compound because you can see in this equation, if this equation is balanced, so we have oxygen here in CO2, we have oxygen here in water. Some of those oxygen come from this compound because the compound has oxygen in it, but some of those oxygen come from what? Come from this guy. This is the air. Alright. So what we do is you use the gram of this compound, and this will be the gram of the compound, which means the gram of carbon plus the gram of H plus the gram of O, and try to figure out a way to find out the gram of O. Yeah. That's very smart. So what you do, so you will take the gram of the total, okay, subtract by the gram of carbon, by the gram of H, then you will know the left over will be the gram of oxygen. Now we stopped here. We have some information of the carbon, of the H in the compound, but not a gram yet. Okay? Now think about what do we do to find out the gram of carbon and gram of H. If we know that, then we can subtract these two information into the total gram, then we will have the gram of oxygen. Right? So what do we do? How can we find out the gram of carbon and a gram of H? Then we can use it. What do we do? Continue with the information right now we have here. Okay, now let's review. So we have three information. And let's see, the number is random. We have the gram of CO2, and we have the gram of water, and we have the gram of this compound all together. What we use is use the gram of CO2 and use the molar mass of CO2 to find out how much mole we have. Then we use this ratio to find out the mole of carbon we have. And so we use that information. The other information in the gram of water, we do the similar usage. So what we use is use the gram of water, convert that into mole of water, then we find out the mole of H. Then you already know the information number 3 is that we want to use the total mass, subtracting by the mass of carbon by the mass of H, then we'll get the mass of O. We're almost there, we can put all these 3 steps together, but we are kind of one step less yet. So what do we do now to find out the gram of H and the gram of carbon?
Convert the moles to grams.
Exactly. You see here, we start here. We have, that means we have the mole of carbon, right? How you get a mole of carbon? By mole of CO2. How you get a mole of CO2? From gram of CO2. Okay? We're doing one more step forward. So that means once you get how much mole of carbon, just use 12.1, multiply the mole by 12.1, you get how much gram of carbon. Even though this step is not really important for carbon itself, but carbon only need how much more carbon. Okay? But obviously need the information of carbon in gram, because otherwise you cannot find out how much mass of oxygen in it. Right? So now what do you do for this, for the H? Find a gram. Use what to find a gram? Find a molar mass. Okay? Okay. So we'll use molar mass, find a gram of C, and use molar mass, find a gram of H. Now once you have these 2 grams, okay, then your gram of O will equals that gram of the compound. Okay? So that's equal that gram of the compound. Gram of O will equals gram of compound minus gram of C minus gram of H. That make sense? All right. So let's see what do we do for those examples. Okay, now let's see these 3 information here in this example. Okay. Let's first find out according to the number I write here, right? So the first information is gram of CO2. How many gram of CO2 we have? Oh, it's right on the line. So let me just start right there, right? Gram of CO2. What's our second information? Gram of what? Gram of H2. How much gram of H2 we have? 0.60033 gram, right? H2O. Right? Number 3 information. How much gram of the compound we have? Okay, very good. So think that sometimes you need to practice, how to like sorting out those informations, right? Right. So once you have these 3 informations, again, what do you do for to use the gram of CO2? To convert into the mole of CO2, right? Okay. Maybe I will release some of those so we can work on this board. So let's see, we are starting from a gram of CO2, which is 2.445 gram of CO2. So according to our map here, we are going to convert into mole of CO2, right? So mole of CO2, from gram of something into mole of something, what do we use again? Molar mass, okay? And you will have 44.01 gram of CO2 and 1 bar of CO2. Right? So this was our first conversion, and you can see this gram of CO2 come out, and you get more of CO2. And remember, our purpose is to find out the empirical formula, which means the important information you need is more of carbon, more of H, and more of O. Okay? When you get more of CO2, that's not enough. You have to use this ratio to find out more of carbon. Right? So I can see 1 mole of CO2 is 1 mole of carbon. Is that right? How I get this 1 mole of CO2, 1 mole of carbon? Just from this formula. Say CO2, C1O2. Alright, so we can stop here like one step, and even though here we will do 1 more step. Okay? But this problem here, we also have what? We also have oxygen in it. 2.445 divided by 44.01. Alright, so you get 0.0. Alright, so we'll do a similar calculation for the H2O. How much H2O we have? 0.6003 gram of H2O. And use 18.02 gram of H2O and 1 mole of H2O. And then we'll use for every 1 mole of H2O, there are 2 mole of H. Right, so let's see what we get. 0.6003 divided by 18.02 times 2. And you get 0.06663 mole of H. Any question about these two calculations? Okay, so exactly as what we analyzed before we do the calculation. Okay. And now the question is, how can we find out the mole of O? Because we need the mole for each of these 3 elements. Then we can have the pseudo formula that will divide by the smallest mole and find out our final formula. Right? So right now we need the mole of oxygen. Well, as I said before, while doing our own story, to find out the mole of oxygen, we need the gram of oxygen. Right? So what we did here is converting these 2 moles into what? Into grams. Okay? So let's do these 2 extra steps. Even though for carbon itself, it doesn't matter, we can remember this number here and remember this number here. Later on, just use that in the pseudo formula. But to get the mole of oxygen, we need just 1 more step. So we say 1 mole of C is 12.1 C, and then we'll do the same. So 1 mole of H is 1.01 of H grams. You can do that. So just write those carefully. See what you're referring to. Right? So you get 0.0673, then just keep it like that, gram of H. And that one 0.05556 times 12.01 equals 0.667 gram of carbon. Alright, so what do we do next? We want to find out the mole of oxygen, because we already have 2 moles. If you have a mole for every element, you're pretty much almost there for the formula. So what do we do now to find out the mole of oxygen? This cell here, right? So this cell here. So this cell here tell you want to take the gram of oxygen or equals the gram of compound. Okay. So now that's right here. So gram of O or equals, let's do the substitution. Gram of the compound is how much? 0.8, 2, 3, and 3, right? So that's a gram. And then minus gram of C, 0.667 gram, minus the gram of H, which is 0.0673 gram. Right? So remember we want to calculate here is a gram of what? Okay, 0.8233 minus 0.667 minus 0.0673, 0.089 gram of O. Okay, what do we do now? What information do we need to finish the program? More of what? More of oxygen. Okay? So we will do something like here. We will have 0.089 gram of O. Okay. So this should be like really like in your habit now. So if you have the gram, you want to get the mole, you just use mole mass. Just again, read the question carefully. For this program, you can use mole mass of what? Oxygen itself, not O2, not O3, just O. Right? You will take a 16.00 gram O and I have 1 more of O. Right? Let's do the divide by 16, and you get 0.00556 more of O. Now let me settle all these 3 information we need. We need more of carbon, we have 8. We need more of H, we have 8. And we need more of oxygen, we have 8. Right? But you cannot simply use those guys to find the answer. So you will just say C becomes 0.05556. H is 0.0663, and oxygen is 0.00556. This is the sort of pseudo formula. What do you do next? What do we do next? Divide by the small. Which is our small? Oxygen, right? So let me erase some of this and you do the divide, and that. I think these few steps is important, okay? And probably just keep it there. So that's changing into C, the smallest one is this one. So 0.0556 divided by 0.00556. And H will become 0.06663, 0.00556, and oxygen is 0.00556 divided by itself. Alright, so what do we get? I think that's pretty much like the 10 times difference, right? Maybe not exact, but I will show you what time you can run it up, run it down, from 0.05556 divided by 0.00556, and you get 9.99. And H you get 0.06663 divided by 0.00556, and it will become 11.98, and then O just become 1. Right? So now this is a good example to see what the time you can run it up, run it down. Right? So I'm going to begin to erase some of those information here now. Right? So for carbon we get 9.99, and for H we get 11.98. Right? So this number is like the difference between this number and the closest unit is 10. And that will give you 0.01. Right? So 0.01 is less than 0.1. I think I will skip those. Kind of, that's so close to 10, just running to 10. Okay? Now this one is close to 12, so this becomes H12. Then O just becomes O1. All right. Question: this is probably difficult to memorize those details, like just mechanically, just make sense. As I emphasized at the beginning, you try to memorize those steps, you try to memorize what you want to do. What you want to do is find the empirical formula, which means you find the mole. Right? So just think about those different ways to find the mole. So we said what over here, you get more of carbon first from more of CO2, and get more of H from more of water. So once you have that two moles, we can get a gram of H, more of H, and gram of carbon and gram of H. Then from that you get a gram of oxygen. Okay, any questions? Any questions? Okay, so if, let's see if you can work on your own to find out, to finish this problem. I think that I can read this, I can just follow it instead. that's okay, this was just like an equation, so we don't need the equation. And now you know that unknown becomes those x, y, z becomes those real numbers. So step 1, step 2, right? Step 1, which one you do first? Step 1, step 2, you can just make your own choice. You can do step 2 first and step 1 second. So what you do is converting those gram of CO2 and more gram of water into more of CO2 and more of water. Okay, so what we get? You get E, and see your calculation, what you get, what is E?
You start with the grams and you convert, and then those are all the things I got, and then I subtracted the grams.
Subtracting the gram, right?
Yeah, the grams, and then that's what you get.
That's the
And
gram
then
of
convert that
oxygen.
to moles.
I divide by 16. I have 3 moles.
And then I do 3 moles of oxygen, divide them.
Okay, so you find out the divide by, you get the largest integer. All right. Let me see, did you convert the gram of CO2?
Yeah.
Oh, okay. That's the more of CO2? So then do the next step. Get more of carbon, get more of H. Okay, seems doing okay. You know like what, basically you know like what you need to do. Okay, so that's pretty good. That's pretty good. Awesome.
Thank you.
Yeah. I'd like to say, you're not really confused that much. You know what to do. But usually that's not enough. You need to do more practice. So you're converting back into grams, right? Okay, very good. You did the work. What about you? Working on it? Yeah, at least you get starting right. Don't forget there is a ratio between more of water and more of H. You have the time to do that, right? So that's a more. Okay, good. You have 3 more. Alright, so assume you get the point across. You know, like what is important for the imperial formula is the moles, right? So just somehow you want to find the mole for each element. What do you find? The E, right? Do you find the answer to E? What's the step you are on? So this is the gram of CO2, right? So take the gram of CO2, that's just replaced by whatever you have. Very good. So you have this is gram of CO2, right? You want to write, see what I did there, like on this, on the top. Yeah. So here is our conceptual plan. And that is what in your mind, but you have to perform those step by step. So what you do is just replace those numbers. So you here, so whatever number of you will do, just, so we don't have 2,445 here, we have 540. Right? You put 540 here. And then you, this number is still the same because it's more mass of CO2. Right? And this is still 1-to-1 ratio. Okay? Try to do this first. Okay? Try to do this step first. And do this step just by simply replace those numbers. Huh? Okay, so let me see the.
We have 2 moles and then per 1 mole.
Okay, so I will give you like one like an example. So we'll start with 540 gram of CO2, and then we'll have that 44.01 gram of CO2 here, and I will get 1 more of CO2. Then I will use that 1 more of CO2, then 1 more of carbon here. Okay. Okay, and you want to tell me what do we get? How much more of carbon we have? 1, 2, and 2, 1, 2, 3. 3. So this is more of C. Right? So let's do the next one. Is 222 gram of H2O. Can you read it? And this will be 18.01, 18.02. That doesn't matter. Gram of H2O and 1 more of H2O. But don't forget this ratio. Okay? So have for every 1 more of H2O, how many more of H do we have? Very good. So what is our answer for this? 0, 1, 2, and 2. 1, 2, 3. Okay, so this is H. Right? Now we have to find out. Another question is, what is the gram of O? If we know the gram of O, we're repeating this few steps. Right? So we'll see this gram of O will equals gram of the compound minus gram of C minus gram of what? Of H. Right? And do we know the gram of the compound? 3.69. Right? Do we know the gram of carbon? Not directly right now, right? So we can take, let's see, we'll take, let me just write here. Just, okay. So I'll take 0.123 more C, and I want to use the molar mass of C, 12.1 gram of C. And so now how much gram of C do we get? Anyone? 1 gram of C. 1.47 gram of C. Okay, so therefore 1.47 gram here.
The mole of hydrogen is 0.246.
Okay, thank you. 0.246. Yes, that's fine. now let me put on the top. I will take 0.246 more H. Now this step is you want to get the gram of H. So even though you need the more of H for the formula, but you also need the gram of H to get the gram of O. And now we know 1 more of H is 1.01. You sometimes might use like 1.08 plus 1 of H. You will probably get the similar answer. So what do we get? How much gram of H? 429.
249, sorry.
Okay, the minus 0.249. For my writing, you see, cannot tell the difference between the gram. Okay, online those the units. Right, so
Oh, you should have
I think I'll change that so you just don't get confused. This is the gram, right? Right, so then we do some learning. How much gram of O do we get? 1.97 gram of O. Right, so then that was the one, I think the second last step. So we'll take this number, we know we have 16.00 gram of O for every 1 more of O. Right, so what, how much more of O do we get? 0.923 something, right? More of O. Right, now we have these 3 more. We have more of H, more of carbon. It kind of those are the very like tedious way, but those each step is you are familiar with. Just as I said, so you sometimes you want to emphasize like what you do, but don't confuse by too much of those. So this sometimes you are just little easier to see with examples because those are very abstract, conceptual. But this is not our final answer. So what you do is use this 3 number and write a formula. Then you will write you will divide by the smallest number. Right? So obviously our smallest number is 0.123. Okay. Carbon 0.123. That means 0.246. The perfect 1:2 ratio, right? So then you will get O 0.123. Alright, so we have these 3 numbers, and obviously after you divide, you will get this number. Alright, I think you, as I said, let's just take these few like CRE, a few examples. And I think those should be enough, but I depend on you to every time you just close the book, close the lecture notes, and do that again. Because you can either practice on little different numbers, but or you can practice on the same number just every time, just starting as new. Right? I saw most of you did pretty good, so you get the conceptual plan, that is pretty good. And you just need more practice. But next section is about the balanced chemical equations. So then just know like when you have a chemical equation, let me emphasize a few terminology. Then I will tell you what to use when you do the balance. Right. So let me circle this one, and this one, and this one, and this one. We call them what? They are formulas. Right. So when you balance the equation, never change the formula. which means if you know what is your reactants, what is your products, you just write out those formulas, never change it. You don't change the CO2 into CO, you don't change H2 into H2O2 to get the same number of O, same number of H. Right? So then what do we call this? Let me change my pen. What do we call this? What do we call this in general? Yeah, this is gas, this is gas. Right? What do we call those two guys? Okay, this is called what? State. Yeah? The state. And we have like 4 common states in chemical reactions. So sometimes we'll see this, and again we'll see this. This is standing for aqueous, which means the compound dissolve in what? Dissolve in water. Okay? Now you know what is S standing for? Solid, and L, liquid, and G, gas. Right? So remember those terminologies. Okay, now let me erase those, and we'll give you 2 more terminologies. What do we call these numbers? These 2 numbers. Subscripts, right? Subscripts, right? And they are in formula, right? Also, never change this when balance equation. Obviously, you have to see sometimes they will change when balancing equations. You never change those subscripts. If you change the subscript, you will change the formula. As we said before, you never change the formula for the reactant or the products. Right. So this number here, anyone know what we call these numbers? Coefficients. Okay. Every formula in the equation has a coefficient. We have 2 coefficients here for oxygen gas and water vapor. What are the other coefficients? 1 and 1. Very good. So this is omit, this is omit. If you don't see anything in the equation, which means 1. Alright. So that is the point I think we want to memorize. So when you balance the equation, and you just adjust, change those coefficients, and to get the same number of atoms. Right. So then you know how to calculate how much atoms from the coefficient and subscript together. You get the total number of atoms on the reactants and on the products. Right. I think for this example, and we can see we have 1 carbon. Right? 1 carbon comes from this 1 methane. Right? So each 1 methane is 1 carbon. So therefore, we write 1 carbon on that side. And let's see how many H's we have on this arrow. There will separate the left side and right side. Right? How many H's we have? We have 4. How we get 4? We pretty much get this subscript here 4 and coefficient here 1. So you get this 4, remember there is 1 here. Okay? So you have 1 times 4. So that's how we get that 4. Now how we get 4O on the left side of this arrow? Again, come from the coefficients and also from the subscript. You can see O is here, right? So O has this subscript 2, and also have a coefficient 2. So therefore, you will take the 2 times 2 and get the 4. Okay. So then this one is straightforward. And how we get this 4H? How we get this 4H on this side? How we get this 4H on this side? So you can see here we have a coefficient 2, and we have a subscript 2, right? Yeah. So this also comes from 2 times 2, right? So how we get this 4O on the right side, on the product side? How we get this 4O? we get this 4O. How we get this 4O? We have the plus 2, right? So how many O we get from this formula? 2. So you can see that. Okay, from this, okay, we will take 1 times 2 to get 2O. Now from this, how many O do we get? From all this together. So again, we will take the 2, this red 2 is the coefficient, right? There are 2 water, and then in 1 water there are how many O? 1. Very good. So therefore we get another 2, another 2O, another 20, 2O, right? So you have 2O, 2O, therefore 2O plus 2O. Okay, so you carry it finally it's kind of like this. But how you get 2, how you get this 2, you take this 1 multiplied by 2. How you get this 2, you get this 2 times 1. So you pretty much have to use the coefficient and subscript. Right? Any questions? So that's what I emphasized before. So we began to learn some of those little details of chemistry. So chemistry has those chemical reactions. Usually we're representing the chemical reaction as in the last equation by the so-called chemical reaction equations. Okay? So reactants, products, formula, state, coefficients, subscript, all those terms. Right? When you study the next chemistry class, like chemistry 1 or 2, there's one chapter called the oxidation reduction reaction. And for those chemical reactions, if they happen in like the water solutions, and there's a few steps you can follow to balance those equations precisely, which kind of like a foolproof method. You just follow like a few steps. That will guarantee you will have some of those steps, but it is kind of tedious. So here, what you do, we don't have those steps, so you will just use those try and error. But I will give you a hint, make our try have less try and get the result real quick. Which means when you have those chemical reactions on the balance, you don't want to use what you're going to learn in Chem 1 and 2. Just identify those elements in it. Okay? So sometimes you might be a little like lucky. If in the chemical reaction you have 1 element and or 2 elements that exist as elements by themselves, then your balance will be much easier, because you can leave those elements that as elements by themselves. Maybe on the see in this example we have 2 of that. Maybe on the reactant side we have carbon by itself, that element. And on the product side we have a cobalt by itself. So when that happens, your balance will be very easier. The hint is you balance all the other atoms. Leave those atoms that appear as elements, or elements. So here this oxygen is an element, but oxygen do not exist or appear by itself on either side. On the left side, the oxygen in this compound. On the right side, the oxygen in the CO2. So you will balance those kind of atoms first. That's the hint in work. Usually will help you like in some of the programs. Alright, so let's use these hints. So we're going to like balance the oxygen first. Okay? The reason is you are going to leave the atom or atoms that exist as element, the last one to balance. The last one to balance. And if you have a two, then you can just leave either one as the last one. In this example, we have two atoms. I mean, two types of atoms. We have carbon, use this as an element. We have cobalt, use this as an element. So you can use either one with the last one. Alright, so we'll first decide that I'm going to balance the O first. Okay, how many oxygen, as is this arrow, how many oxygen on the right side, how many oxygen on the left side? This is not O, this is what? This is cobalt, that's C little O. Okay? So how many oxygen on the right side right now? How many? 3 here, right? Right. So how can we balance between 2 and 3? Yeah, that's the usual technique. You find out, the cross multiply. Okay. So therefore, the 6 will be the number you're going to think about, but don't use 6. That means how can you get a 6 from this? So what you do, you will put a 2 here. You will put a 3 here. Because those are the so-called coefficients you can change. Right now, that's our first try is like that. So sometimes you might have to adjust again. You try that, it doesn't work. You can even use the fractions. So right now we just use integers. You can use any number at the beginning, but so later on we want like only have those integers for this traveler. Later on some other traveler you can have those fractions. Okay? So now we balance. Now let me erase those. Okay? So we already balance O. I put a 2 here. I put a 3 here. So then next we can either balance carbon or balance cobalt next. That doesn't matter. Just as long as you have one that that the last one can balance only like itself. And now let's try to balance the carbon now. Okay? And how many carbon? Let's see on this side. How many carbon on this side? How many carbon on the right side?
3.
3 carbon here. How many carbon on the left side? 1. See, that's the reason you leave that the last one to balance, and your choice is not easy. Because here just by itself. You can just simply change this 1 into 3, then you have the same number. So therefore I will just put 3 here. Alright. Now let's do the same exam. How many cobalts the CO we have on the right side, how many CO we have on the left side?
4.
Very good. How we get a 4? Yep, coefficient subscript. See here you just, so we notice coefficient 2, and we have subscript 2, so we have 2 times 2 get a 4. And here cobalt exists by itself, just very simple. So what you do, you put a 4 here. And then just exam. Usually, if you off balance something, like in your second step, you might off balance what you already balanced in the first step, and so on. So you usually do a wrong check. Okay? So I will do the check for yourself. I think this is balanced. So another example is perfectly tedious because in this example, so I don't give the equation, but I give you the chemical reaction in words. So what you do, just write out the equation first. Right? So we know we will have the reactants on the left side, and then we will have the products on the right side. Right? So let's read the question carefully, see what are rectangles. Okay, very good. Butane, that is C4H10, and it has gas.
Oxygen,
Very good. How do we know we have oxygen?
they combine with oxygen, so it just says it.
Yeah, usually this word, right, means combine with oxygen. Right, so these are the two rectangles. Right. What are our two products?
Carbon dioxide and gaseous water.
Yeah, so that is the equation we use. I remember the equation I use here. I write like these two products, the CO2 and the water. And the other one with the H2O gas. So I make the problem a little bit tedious because the question tells you what are the states, tell you the gaseous butane and the gaseous CO2 and the gaseous water. So therefore you put those states on, it's a little bit tedious, but the fundamental, the principle are the same. Right? So once you identify what is your rectangle formula, which is C4H10, and the other formula is O2, and then you have the two product formula, then you never change those H2O, you never change those CO2, but you can only change, right now we're assuming everyone has a coefficient of 1, but you can adjust 1, 2, 3, and so on. Right? So then the other hand is leave that one type of element of the last one to balance. Which one you want to leave as the last one to balance?
Single element.
Yeah, the single element. So in this example, what are our single elements? Oxygen. Right, so then you can choose, we have three elements. We have carbon, we have hydrogen, we have oxygen. You can choose either one to begin with. Okay? So let's start with what? What do you like to start with?
Carbon.
Let's start with carbon. Okay? So let's do what we did before. Let's examine how many carbon we have on the left side, how many carbon we have on the right side, and just use the coefficients. Right? How many carbon right now we have on the left side?
4.
Oh, 4. And how many carbon right now have on the right side?
1.
Okay. So all the carbon are here. That's probably you just probably you review what we did for that program and those calculations for the numerical formula. You have a better understanding. So all the carbon here, they all get into CO2. Because in the other products is H2O. You don't have carbon at all. Right? So if you want to have 4 carbon, and what you do is just put a 4 in front of CO2. But the problem is once you put the 4 in front of CO2, that means it will apply to everything here before the plus sign. Right? So let's just forget about that oxygen. Now let's see that as the H. Okay. How many H we have? How many H we have on the two sides?
10
Very good, 10 and 2. And all the H, that it also is kind of similar. All the H here is in this water. And that's the reason we do the calculation. We just use information of water, get more of water, and then get more of H. Right? So then what do we do to change that 2 into 10?
Throw a 5 in
Let's throw the 5 into the about 1. So we'll get this, we'll get a 5 here. See that goes, right? So now we only have one that is not balanced. So we'll see how much O and how much O. Right? So what you do, you are adding up all those O that's on this side that's not because this as a single element, and then you can adjust the number here and make the number the same. And that's the reason we leave this one and last one to balance. How many oxygen we have on this side altogether? And then just figure out that from this guy altogether here, how many O do we have?
8.
Very good. See? And then altogether here, how many O do we have here? 5. So then adding that together, right? You get 13 O here on the right side. Right? So then how can you make a 13 from 2? Because on this side, you cannot break this 2 O2 into like a single O's. So how can you make a 13 from this 2 as a pair? Then you can use any numbers. You can use any numbers even though you don't want to keep those numbers as your final answer. Right? So you can, for example, you can use like 13 over 2. Right? Yeah, because once you have 13 over 2, which is the coefficient, and as we do before, we want to find the total number, you will take the coefficient multiplied by the subscript. The subscript here is 2. And then we know that 13 over 2 times 2 is 13. Right? So therefore, so we have 13 here, like this. Okay. The so-called conventional chemical equations don't use fraction as a coefficient, but when you study that chapter 6, and you can use it for some of those particular chemical reactions. So you can change those fraction coefficients into integers very easy. You just multiply every number by the denominator. Right? So right now we have this equation, and in this equation, it's balanced if you check. Every atom is balanced. The problem is you have a coefficient here which is a fraction. So what you do, conventionally, you don't want to use those kind of formats. In chapter 6, you can use this. Right? So then what you do, just multiply everything by the denominator. On a common denominator, you have multiple fractions. So what we have here is one denominator, is 2. So again, that means you will multiply this into all the what? All the coefficients. And you don't have to bother with subscript. With subscript cannot change. Alright. I think that's it. So what that means, you will get, let me write that at the bottom. 2 times C4H10 gas plus 13 O2 gas, and then we'll produce 8 CO2, and then 10 H2O, but then I forget the state. That make sense? Alright, see, you can do a practice. What I tell you is a hint, right? So you can balance any atom first, but at least you will leave one atom which is a single element, and in this one we have a few. We have 2 atoms that is like a single element. Yeah, the answer is E. Yeah, how do you get E? I know for these kind of problems, if I give you these few answers, you know, like one of them will be right. What you do, what you might do is try all those different ways, right? But then for next problem, it will not work because next problem, your choice is not all those answers, is the ratio between 2 coefficients. So now let's do it together, see how we balance this problem. So as I said, we have 2 atoms that is a single element. What are the 2 elements that is single element? What are the 2 atoms that is single element? We have N and O. Okay, you can choose either one as the last one. Okay? You can leave any of these 2 as the last one. Okay, now because this O is the last one written, so I'm just starting from the left side, one by one, balance each atom. You can use any numbers as a coefficient right now. Right? Okay, now how many N we have on the left side? So how many N? How many N right now? How many N on the left side? 3. Okay, so you want to balance this N has 3 without changing anything else. That is the advantage of those some of the elements that are by themselves. Right? So what would be the best choice to make also 3N on the right side? You have that 3N right now on the left side, but on the right side you have each N appears as N2. You cannot break that N2 into like an N1. So how can you make a 3n from, how can you make a 3 from 2? Huh? Very good. So you have like a 3 half like this. So what I do, I will put a 3 half here. Huh? So as I did it before, if I have this, which means I will take the 3 half, which is the coefficient. So let me rewrite that. Coefficient. Remember you take the coefficient, multiply by what? The 2 is what we call the 2? Subscript. Yeah, you always take the coefficient, multiply by the subscript to get the total number. Maybe give the subtotal number, because you might have like 2 formulas give the same element. I do the same for each formula, add them together. Right? Everybody understand? Does that make
Why
sense?
did you do 3 halves?
Because you want to get a 3 without off balance something else. Okay? You can do something what we did before. You can, what we did before, I saw like Patricia, you can put a 3 here, you can put a 2 here. Okay? Now let me erase all those. Okay? What we did before, if you want off balance, you do that. So what you do, you put a 2 here, you put a 3 here. Okay? Then auto balance. Okay? Well, you can imagine that once you do that, you don't want to have that 2 in front of that. Just divide everything by 2. Okay? That is one way to balance. But in that way, when you balance, you just try to change as less as possible. Okay? Try to change as less as possible. Well, what I mean is, in this step, I change 2 numbers. I change this one into 3, change that one into 2. But if I can change only one number, I just change one number. Right? So if I put a 3 and 2 here, then you know, if I put a 3 half here, 3 half times 2 gives 3. Right? Okay. So now you also have a balance equation. Now you also keep in mind, you don't want to have the fraction like this, but you can change that very easy. You just multiply by the denominator, maybe the common denominator. So let's keep going. Okay? So we just balance one by one like this. So next, let's balance something like, you are still keeping in mind, you don't want to balance O because O is a free element. Right? So leave the O, the last one to balance. So therefore, you examine the next one, that's CO2. That means if you don't want to balance O, you want to balance C. So how can you balance C? How many C right now on that side? 3. You want to have a 3 C, right? Right now there's 1 C here, right? What do we do? Just 3 here. So now let's try to balance the next one. Try to balance H. How many H here and how many H here? 5 H, okay, and 2 H. So what do we do? 5 half. 5 half. So what do you do? You put 5 over 2 here. Alright, so far so good, right? We balance all the elements now. Okay? Except which element has not checked yet. We don't check oxygen yet. Okay? So therefore let's check the oxygen and see how many oxygen on the right side, how many oxygen on the left side, and how can we make that equal. So how many oxygen on the left side? 9. Now on the right side it looks tedious. Okay? I choose this example because I want to emphasize that principle. So you want to leave like that atom that as a single element, the last one to balance. In this example we have 2 of them. We have A and we also have O. So therefore we choose, we can balance the N first, but at least we have another one, so we'll leave that one and last one to balance. Right? And the other technique is you can use fractions. Okay? So I'll give you like, so altogether I'll give you 2 hints. So leave the free elements, the last one to balance. The second technique is use those kind of guys. So even though you will not see them in your final answer, but beginning with this. Right, now how many O right now on this side? Forget about this one first, because this one is the one you can tune it. You can tune it to add up together to get the total number. Now before this one, how many we have? How many we have from this guy? Very good, 6. How many from this one?
2.5.
Yeah, you get 5 over 2 times 1, which equals 2.5. Alright, so don't worry about those looks strange that you have a 6 plus 2.5, so 6 plus 2.5, that becomes what? 8.5. Okay, so we have 8.5. It's from, not really, so let's see this question mark because we did not include this one yet, right? So then the problem is, you want to make up everything together on the right side become 9. That's the purpose to leave this as the last one because you can use any number. So then you know how much do you need now to make that total equal. How much do we need now to make that 0.5? Okay? Right. So then how can you make a 0.5 from 2?
1/2.
Right, that's 5. Well, you mean one, you mean 1/2, right? So you mean like this, right? Yeah. Right. So then, looks like a string, but it's balanced. So you can see this 1/4, this 5/2, this is 3, this 3/2. So anyhow, anyway, but right now I said you don't want to use those fractions, right? So here you have a denominator is 4, and the other 2 fractions have a denominator is 2. What is the common denominator? What is the least common denominator between 2 and 4? It's 4. Okay? So if you multiply every number by 4, every number becomes integer. Right? So I will keep those numbers. So therefore I will put this in bracket and I will times 4. Understand? Yeah.
What's the fourth from
This one? Okay. See here is 8.5, very good. So I want you to don't do that. Just ask me. So you have a 8.5 and 9, right? So the difference 9 minus 8.5 is 0.5. So this much O is needed on the right side. Well, where this 8.5 come from? 8.5 come from this one and from this one. We did not count in this one yet. Right? So therefore, we only need half O from this. We need half O from this last one. Okay? So we need half O from this one. Okay? And so let's see this coefficient. So let's say we don't know that. And we call that x. Right? So x times 2 is 2x. Right? So 2x, you want to get what? How much more O do we need? Oh, 0.5. Right? I mean, the problem becomes so tedious. Now you can find out what is x. So 2x equals 0.5. Divided by 2, and then x, the 2 and 2 cancel out, x becomes 0.25. 0.25 is what? You can keep 0.25 here, or you know 0.25 equals 1 over 4. Alright, so after we multiply, this becomes 4, this becomes what? 6, this becomes what? 12, and this becomes 10, and this becomes what? 1. Alright, so therefore the answer is E. You understand now why we use here, why we use 1/4 here? Okay, so once you use 1/4, you remember we find out the numbers by taking the coefficient 1/4 times the subscript. Okay? And now once you put it here, so 1/4 times 2 is 1/2. 1/2 plus 2/2 is 3. 3 plus 6 is 9. That gives you the same numbers. Right? The principle is very simple. You just try to get the same number of O on the left side, on the right side. And we get this 8.5 from these two guys. And this one as like what we call that? As a free player, because you can change this one into any numbers and you make the total equal. A free person. Remember that? So this O2 is like a free person. Can be either like the what we call that? The point guard or the forward, right? Or the center. So do practice. I think you understand the principle. Right. So this is similar. This is similar. Do practice. So let me see what's which element you balance the last one. Oxygen. Okay, you remember that technique. Okay? And so then you can also remember the other technique, which means you can use a fraction or those decimal numbers. You don't have to always use at the beginning. You don't have to always use those integers. Okay, you can balance the carbon first. Then you put 5 here. Okay, so then both are equal, so we put a 5 in front of both of them, right? Then last one with the O. You know how many total O do we have on the right side? 15. Yeah, very good. Yeah, very good. Very good. Yeah. What is the ratio between what? Between oxygen and water. All right. So what's our technique? Which one abandon first? Whoever gets his number right. Huh? 1.5? Yeah. Very good. You get a 15, but then I think that you not use, you already have that 2. Or you can, if you don't have the 2 here, the sum is 1. Then you have 15 or 2. Huh? Then you multiply it by 2, so then this 2 will come out. What do we get? 10? Need help? You need help? Need help on this one? Just write on right. Write on the last one. Write on the last one. See that this is 26. So this will be. Oh, I think we run out of place. You want 26, just write at the bottom. 26 is T. Yeah, it's T. T is like
You should have ran out of.
so sort of like a sign is on the 24, right?
That was number 50.
25.
Yeah, he started at 6.6.
Right. So what you did is, I think most of you guys right away, right? So you put a 5 here,
He just said.
and you will put a 5 here. Understand? So then what are we starting from? We have 5. So then we'll have a 10 over here, 5 here. Together we get a 15. You want to get a 15 from this side, you get a 15 over 2. Right? No, you want to find the ratio, you can just take this number. You want to take a 15 over 2. Right? Then divided by what? Divided by 5, because you want to find the ratio, that means you just take the number divided by 1. And this will come out, you get a 3. That means you get 1.5. Or, if you have this number just not a usual number. Just multiply everything by 2. Right? So I take the 2 here, and this becomes kind of out, and this becomes 10, this becomes 10. Right? So we can do that. Alright, any questions? So let's turn in the scantron for chapter 3, and I will give you the scantron for chapter 2 you can use for chapter 4. Okay, so put your scantron here for chapter 3. So the last one you can just write number 26, and then just write that. Don't use the 51, don't use the other side. Don't use the other side. No, don't use the other side. So you write so your right arm at the bottom, right 26.
Okay, so right down.
Alright, so everyone don't use the other side, don't use the 51 or 52. You can just tell me the answer on this. 26.
Dude, it might as well be in Spanish at that point.
26, 26.
I get home and it's like, okay, I'm starving, but it's 10 o'clock. So,
Just go with the flow.
Alright, now, think of that scantron for chapter 3.
I'll get yours, Bradley. Stand by me next time. Appreciate it. Oh, shit.
I'm not gonna do this, so.
You see it right
regular last one.
Too late. Sorry, Brad.
Bradley, Becky could hook me up, so it's good. I mean, she's so cool, it's all good. I always forget his name. His name is Brad. It's just, we all have so many names. We need like different cards to make stuff different. Yeah, that's why it's memorable.
How's it going back?
What's your name again?
Sam.
Sam Watts?
Yeah.
Maybe you're like your trusty sidekick. So if I ever just ditch out and give up, you're just gonna carry me on the fucking mountain.
I guess so.
Got it.
That's where this is going.
That is.
Okay, so this is chapter 4.
Let me down. Grant told me drop this. You'll have to carry a drum.
Yeah, I can do it.
Good.
Hey, did you guys hear all that?
Oh. No, did you?
Dom,
No. I thought you guys did.
June,
Did you even start this?
Jack,
No, I meant when No, dude, I don't, you know, are you going to figure it out?
No.
Who is? They're gonna, we were talking about, because I was gonna talk about it afterwards, I don't know what the fuck he actually wants us to do. We do?
And you don't just have to fill out that graph.
Bitch.
Yeah.
Procrastinating doesn't work, dude.
Yeah,
Okay, everyone get the schedule of chapter 4. We use chapter 2 schedule of chapter 4.
So Google how to write Latin reports.
Basically.
No, I'm just.
Yes, sir. When I write up a lab report, I'm gonna have to say we fucked up a client.
Really? Why is that?
I don't know, don't you have lab reports? Did you say? We were fantastic. We mixed this chemical with this chemical, this happened.
Then we'll start on 21. Let's start on 21.
The instructions were like this and this.
Okay? We have practiced one. We heard you want to explain the show like you
Have our names on it? Not
You're not even, me neither.
Well, I'm gonna figure it out, but I don't even.
I feel like we're all supposed to stay on that last one.
Okay, everyone get the schedule for chapter 2. Use the schedule for chapter 2 for chapter 4. You start on 21. Start on 21 for the first one. 19?
Okay, yeah, so it's 20. Before we get confused.
You don't have any more on mercury?
So I'm not going to start on this stuff.
Yeah, we know. Nothing else. You can write it.
Oh, okay.
For them, how you write it?
I would.
Yeah.
No, he said he was gonna say it Tuesday.
I will, I can. I'd say.
You'd have to write it. You'd have to write it.
Studying, I go, where you studying from? You will see the name?
You know how they
I wrote the last one.
they have like those machines that have coffee miles.
Right, you may have had that, that's.
You will see the name.
They have coffee machines.
Yeah, the ones you just put money into and makes it a pop.
Yeah.
Yours, T buildings out? Yeah, it's right in the T building. You walk up the ramp and walk through. Oh, it's right there. Yes.
No, dude, it's actually.
Alright, so now let's start on chapter 4. Get some So in chapter 4, you pretty much continue with, okay, so everyone, you are going to continue on those, concepts like modes and grammar conversions. Okay? So adding like a few more of those conversion steps. And in chapter 3, chapter 2, we learn a little bit of those conversion like between different materials. For example, we use gram of CO2 and get more of CO2 and get more of carbon, right? So we already see some of those tastes of some of those. Well, you're going to see like a lot of more like in chapter 4, right? Because in a chemical reaction, once you see in a chemical reaction, like in the last few program of chapter 3, the equation is balanced, and so that those balance equations, those coefficients, give you the more ratio. So therefore, everything in the balance equation is related. Okay? So that is based on the conservation of mass. Right? So then the study of those numerical relations of those chemical quantity in a balance equation is the main focus, one of the main focus of this chapter. Right? It's the main theme of this chapter. And we call those kind of calculation is stoichiometry. So the coefficient, as I emphasized before, in the balance equation specify. So that a few words in the first slide is related and numerical relation. So it's very important. Those numerical relation, you get those numerical relation from those coefficients in the balance equation. Okay, so don't worry about that, and you will see like more examples that will help you to understand what we mean by the related and what we mean by the numerical relations. These words, the study of those numerical relations in a balanced chemical equations. It's very important to use the balance equation. And as we learned in the last chapter, when you have the equation, there are a few terminology: the coefficients, the subscripts, the state, the reactants, and products. Right. So if I give you an equation like this, and you can easily identify, let me circle all those coefficients here. Coefficient for this octane is 2. For this oxygen gas is 25, for CO2 is 16, for water is 18. So this few coefficients, it will specify, what we call is very, very important later on, some more ratios. Even though sometimes you can understand those ratios as molecular ratios. So once you have those ratios, and you can use ratios as what we did here, you can see ratios between CO2 and carbon is 1:1 ratio. That ratio comes from the formula. The ratio between water and H is 1:2 ratio. That comes from the formula. You can get those ratios from different places. You can get the ratio from the coefficient. And sometimes we call them molecular ratios. Sometimes we call them more ratios, depending on the problem. Alright, so you can understand those few numbers as a ratio, which means whenever you have a 2 that octane, it requires 25 of O2 to make the reaction precise, the word completely matching up. And if you have those kind of chemical reactants, and the ratio, those kind of ratio, we call them stoichiometry ratio, which means their amount is exactly the ratio specified by the balance equation ratio, coefficient. Right? So you have quite a few numbers. You can see the ratio might be between like 2 and 25. If I want to get the relation, if I want to get the relationship between this octane and O2, I will choose these two numbers. If I want to get the relation between CO2 and oxygen gas, for another example, so I will use 25 to 16 ratio. You can choose any pair of those formulas in the equation and find out what are the ratios. Right? So the ratio or relations is very important in the first 4 chapters when I emphasize in this class, because once you have this kind of ratio, you cannot have those equation. And if you have an equation, you can have two fractions. I think you already know the usefulness of the fraction. By the conversion fractions, this is conversion fraction, those are conversion fractions. It's very useful, it's kind of powerful in this chemistry class. Right? And you can understand those as more, as I said before. Okay? Because more is just a unit of a very large number. So you usually do not want to counting like one molecular, another molecular. So usually counting by how much more, how much like the chemistry doesn't. Right? So then your ratio number is still the same, just different unit. Right? Understand? So if I have those equations, I tell you with the balance, you can have many pairs of those ratios. Okay? And then once we can recognize what is the ratio between what and what, then we use it. So the amount of any substance in a chemical reaction can be determined from the amount of just one substance under some conditions. If you have more than one substance in the more than one reactant, more than one product, under some conditions, which means that you are assuming the other one do not have any limitation on you, which means the other one is excess. Sometimes I will give you both informations. Okay? So this word is relatively speaking. Okay? So you can find out the amount of something else just from the amount of one, assuming all others have no limitation, just two players, 1 to 1. Right? So for example here, if I tell you we have 22.0 more of this, and I ask you how much more of CO2 you can produce. Okay? So this, as I said, relatively speaking. So from this information, you can find out some information, which means to the maximum, how much you can produce if you have this much of that octane. Okay? And obviously, to produce CO2, you not only need octane, you also need this oxygen gas. You don't have the information about oxygen gas. For those kind of problems, just assuming you have enough oxygen gas, enough to use up all those available octane. So therefore, if I tell you only one information for one reactant, and you want to find out how much you can produce, it's relatively easy, which means you're assuming the other one is in excess, will have no limitation on your calculation, and then you just find out you have the information about this C8H18. You want to find out the CO2, just examine this kind of equation and find the number for the C8H18, find the number for this CO2, and make a proportion like this. Right now, this is just only a proportion or an equation, but you decide what you put on the top, what you put at the bottom. Okay? So as I emphasize from this first few chapters, you decide because you can decide what you have. If you have that more C8H18 and you want to get more of CO2, so our old technique, which means you want to cancel out that out, right now that on the top, so therefore you put this guy from this ratio at the bottom, and in this way you can cancel out what initial you have. You see, nothing new, just something like you familiar with. right? So it's a very typical conversions, typical technique, okay? But you get those information from little different place. So if you can read those chemical equations, so what are the coefficients, what are the subscripts, what are the formulas, and then you can use it to the conversions. Right. So the last example just give you the key step. Okay? The very, very important step in like this few chapters, in this chapter and so on, which means more of, let's say more of something, we call that more of A, okay? Change into more of B. In the last example we used more of C8, H18, and change into more of CO2. In general, you can have any more of any compound in your chemical equation. If you know the chemical equation balance, you will find out those numbers and do the calculations. And this, what we can call that is the key step of the bottleneck. Okay? So once you know this step, you can convert in between any two substances. Okay? It's more to more conversion in this key step. Okay? So then we will get different way to get the more of A. There are a lot of different ways to get more of A. Then you can use more of B and get a lot of other information. Okay? Now so far, what we learned to get more of A is use gram. And so far, what we learned, once we have more of B to get some other information about B, is to get a gram. So as you learn more chapters, and you will have some other way to get more of A. And once you get more of B, you can get other information about more of, about B. Right. So right now let's see more. Okay. So if I forget about those other different ways, right? And our typical calculation for so far, it will be gram of A change into more of A. That's typical. If you don't know that, I think that's you're lying. You know that. You know, like if you have gram of A, and you should be able to use more mass and convert into more of A. Okay? So what you knew in this chapter is use those coefficients from the Banton equation and get more of B. That's what I said the key step you learn in this at the beginning of this chapter. Right? Now once you get more of B, you can continue get gram of B. We'll have a few new steps, right? So as we emphasize in the first chapter 2, chapter 3, so between gram and more of the same substance is very, very important. What we did in chapter 2 is that you want to get more of A, you can get a number of A. Now here we're doing several different directions. So once you get more of A, you can get more of B. Once you get more of B, you can calculate the gram of B, or volume of B, pressure of B, and so on. And obviously that makes sense because you want to know like how much gram of something you can produce from how much gram of something. Okay? In this example, so we'll be able to starting from this example. So this example is you have this chemical reaction equation with the balance and tell you some plant consuming this amount of gram of CO2, which is as reactants, then ask you how much gram of glucose or mass of glucose you can produce, and then obviously you have two reactants. Did not have other information, other exact information about the other reactants, but tell you have more than enough of water. So therefore you don't have to worry about H2 or the other reactants. Okay? So our conservative plan, you already saw that before, I'm gonna skip that. So I'm just starting with 37.8 gram of CO2, right? And I'm gonna first convert this gram of CO2 into mole of CO2, use the molar mass of CO2. Now you know molar mass of CO2 is 44.01 gram of CO2 and 1 mole of CO2. Right? So this step, I think is already kind of like your second nature. It's just, you know, like whenever you have gram divided by molar mass, get a mole. Now the problem here is mole to mole ratio. So this step is new. Okay? Now we want to get something about this glucose with C6H12O6, right? So that's the in our mind we want to convert it from mole to CO2 into mole with this glucose. So we just have to find out these two numbers here from this equation. Okay? So what is the number of for CO2? What is the number for this glucose? 1, and then this is what? It's 6. Right? So you can see this comes out, this comes out. Okay? So then next step, you will see this, and right here, probably 1 mole of C6H12O6, and how many grams of C6H12O6? And what do we call this? What do we call this? How much grams? What is this? Molar mass. Okay? And molar mass of this, I think, what is it? I think 180 something. 180 grams. Okay? Right, so then this will be the setup. Okay? And you can see that you have 3 steps. Okay? And 2 steps is kind of review. Molar mass step. Right? Molar mass. And this is the only new step. Right? So these 2 steps, in our molar mass. What are we using in this step? What is used in the second step? So once you have this, and this area will be very simple. Right, I think that we were also prepared for the lab like Saturday, right? Just get the lab menu, read the lab menu, and see if you have a question, and do the question.
I'll make sure I do the lab on Monday. Just in case Carlos doesn't show up for any meeting. Carson said he was going to show up on Thursday. You better see lab report.
I have like 5 more science classes and then 2.
Did you get my email? Yeah. I didn't know what I meant, yeah. I knew well, that number was like, oh. The number was on the whole capsule. Like I said, I didn't know what to do. And then I put in that sheet. No one did. And they were both going around, and I took really good. He emailed it to me, so we're good. That's the right number, though. This is that's the right test number.
That's what you told me, and I never believed that.
Oh, it's my report. No, my conversation. Oh, it's because my phone was so yeah, I can make an exception. Let me find it out. I posted on Facebook or something. Oh, you got me on Facebook?
Is that the wall?
Yeah.
Alright, well, let's get it.
No, I should have a conversation. Oh, yeah, the group conversation.